To the solution for Codemasters 2016, question 5. I'm Andrew Turpin from the University of Melbourne. So question 5 continues on from question 4, and it talks about this latitude and longitude file and building a wall around all of the dots, all of the houses that have the disease. This is an example of a convex hull, is the name of this algorithm. Now the question doesn't actually ask you to compute the convex hull. That would be containing Chris's wall. It asks you to compute a slightly easier wall. So let's have a look and see what we could do. So first of all, the first question says, if we have this convex hull, or a wall around all of the points, what's the longitude of a house? What's the smallest longitude of a house that's on the wall? So if we just think about it for a sec, so maybe let me just generate a random field of dots here, and we can have a look. So here's a random field of dots. If we're going to draw a wall around all of these dots, the smallest longitude would have to be that of the leftmost dot, right? If the wall didn't go through this dot, if it went through this dot and this dot, then this would be outside the wall. So the smallest longitude in the whole set has to also be the smallest longitude for the wall. How do we find that? In R, we would read in the data file, and we would find the minimum longitude, which is column 2. I thought it was column 2, but I forgot to skip the first line, which tells you how many lines are in the file. So there's the smallest longitude, and the second question asks what's the largest longitude, and so by the same reasoning, the largest longitude has to be the rightmost point, because if there's not a wall, if the wall doesn't go through that point, then it's going to be outside the wall by definition. So we need the maximum. That again, Excel could have given you those. They have to be rounded to do decimal places. Now the interesting bit. So the smallest latitude. What's the smallest latitude? That's not an interesting bit. That's the minimum of column 1. Hooray. So, Practical Pat thinks that Chris's wall is too ambitious and wants to build a wall by connecting the following 4 houses. Smallest longitude, largest longitude, smallest latitude, and largest latitude. So if we go back to our little dot screen here, what's going to happen is that we're going to choose this point here, the one with the largest latitude. We're going to connect it down to this point over here with the smallest longitude, then down to this point here and over to this point here. So we're going to get a square, but there's going to be some points left outside of this square. So how could we work out the distance? We just need to know the coordinates of these 4 points, and then we can directly do Pythagoras on those, the Euclidean distance formula. And the question asks us here, what's the length of Pat's wall? And in degrees, doesn't actually say in degrees, but that'll be the easiest. And so we could work it out in degrees. What will that be? We have to find these locations, etc., etc. So you need a bit of code, a bit of searching around to find these 4 points, and then you just use the square root of x squared, x1 minus x2 plus y1 minus y2 to find the distance. Question 5 is the really tricky one. How many houses would be outside Pat's wall if it was built? So going back to our little example here, if there was a line going from this dot here up to this dot here, then we can count there's 1, 2, 3, 4, 5, 6, 7 points falling outside the wall on that angle. Then we know that we're going to connect from here down to here, and then we've only got 1 point. And then from here over to here, maybe it's about 10 or 15 points, and here to here, another 10 to 15 points. But how do we find these points algorithmically? Well, what we can do is if we run a line from here to here and compute the angle of that line from horizontal, any of the points that fall outside the wall must have a bigger angle than the one that the wall has. So what we can do is we can compute this angle here using arctan, and then we can compute the angle for all the other points. So a for loop over all the points computing the angle, and if the angle is greater than this one, then it must fall outside the wall in this direction. Similarly, we can compute the angle from the leftmost point down to the bottommost point, and we can say I would compute all the angles again for all the others. Any of the angles that are smaller than this angle must fall outside in this quadrant. And then we can do the same from the rightmost point to the bottom, compute the angle, count the ones that fall outside that angle, and from the rightmost up to the top, compute at that. So for loops, computing angles, or you can be a bit smarter about it, but it doesn't really matter. It's fast enough if you do it brute force-ish. Computing the angles from this point to all other locations and seeing if they fall outside the wall and add them all up. And that's one way you can go about doing that.